All right, hello everyone. David Duff here, and today I have Science Side Up with me. Um, Thank you so much for joining me. Um, just wanted to point out that my partner found this pen and got it for me. Do a personal thumbs up for evolution.
I love it. And
Yes, I
I
love it
am,
also.
as often when I am on live streams, I am joined by the sweetest cattle dog. This is Chester.
Aw, what a
Um,
sweetie.
so he's a
Aw.
little boy and he needs cuddles. So if that's if you see me petting a dog right off stream, that's what I'm doing because he is
Aw,
very good.
such a cutie.
Yeah.
Be sure to give him a milk moon for me.
Oh, of course I will. He's so good.
So, as I understand, you just reached 1,000 subscribers. So, thank you. Congratulations on reaching 1,000.
Thank you. Yeah, that's I've been on YouTube for a couple of years, and as I'm sure you've learned, growing a science communication channel is difficult. But turns out if you go debate a flat earther and they're sort of a jerk to you,
Right.
a lot of people will come over in support of that. So
Oh, yeah, definitely.
yeah.
So feel free to introduce yourself. I know from what I understand, you're a graduate student studying meteorology and climate science.
Yeah. So, guys, I'm Maddie. You can find me here on YouTube at Science Side Up. I talk about all different kinds of science stuff. That's because I have a sort of broad science background. I have a bachelor's from MIT in math and Earth atmospheric and planetary sciences. I was the nerd that double majored. And then I ran off and joined the Navy, and I spent 4 years as an instructor at nuclear power school. So I taught the basic principles of nuclear propulsion and nuclear physics. So I have a weird background in nuclear stuff. And then I started graduate school in meteorology. I got my master's degree a couple of years ago, and I'm working on my PhD. And so that I specifically study the interactions of weather and storms in the Arctic and how they affect sea ice. But I'm at the University of Oklahoma, so that's out here in Oklahoma, which is just Tornado Alley. So we inadvertently study severe weather quite a bit.
Oh,
Not
that
even
sounds like
inadvertently,
fun.
but it's a you can always jump on a tornado research field campaign if you've got nothing else to do over the summer. So it's a great place to be to study the weather.
Oh, yeah, definitely. And I'm David F. I know we met on the Dapper Diner stream, on the marathon debunking of Genesis apologetics.
Mhm.
Um, I am a biology major at the University of Maryland, Baltimore County. So I'm thinking about doing a double major or doing a minor. I know I'm going to do a minor in music, but I don't know if I'm going to
Okay.
couple that with a double major or not. Um, so my interest is in um, evolutionary biology and genetics and that type of stuff. So that's the side
Yeah.
of the stuff I like.
Well, that's awesome. My perhaps bad advice is I did not intend to double major. I came into MIT wanting to be a math major, um, and got into a research project that was in planetary science and took a couple classes to support my research. Realized that I had already earned a minor, and then kept taking classes in that department because they were nice and gave me cookies. And then I realized I was like 2 classes away from a double major. So that's the story of how I accidentally double majored and learned about, I got to take a geology class. Geology was the one class away I was from getting my double major. So
Yep. Yep. And that is pretty interesting. So you've recently been putting out some videos on climate science and doing some debunking of young Earth creationism, especially people like Dr. Andrew Snelling and others. So go ahead and why do you feel that it's important to respond to young Earth creationism?
yeah, so for me with young Earth creationism, I what I find really it's one of the places where um, there's a lot of access to bad information, and sometimes that bad information is like more accessible right? And I think one of the things that scientists can struggle with is explaining their field of expertise in a way that's actually understandable, in a way that's accessible. And so, be it with climate science and weather stuff, or young Earth creationism, I think it's really important to make good information be as easily available and as accessible and as understandable as bad information. And so that's really what I try to do with my channel. And one of the reasons I specifically respond to I got a little upset in my live stream where I was debunking some stuff Dr. Andrew Snelling was saying. And that was because I kind of realized in that I think he knows better. And I think it is my opinion that he is kind of intentionally misleading, or at least knowingly misleading people.
Yeah.
And that
So,
just feels icky to me. And that makes me angry, and it makes me want to combat it.
right. So in other words, lying to the global creationist audience, and he knows that his audience isn't going to go home and try and fact check what he's saying.
Yeah, yeah. And the things that he's kind of the thing that I specifically thought he was being deceptive about was he said that that his research group had found carbon-14 in a coal sample, right? And the only reason that I figured out that wasn't really accurate was I dug into the methodology and the measurement section of how radiocarbon is measured for carbon-14 dating, and realized that oh, they don't actually put it through a mass spec and see the atoms, right? And say, oh, yep, carbon-14 right there, right? They just measure the radiation that comes off of it. And so saying that they found carbon-14 is actually incredibly misleading, because what they would have found was, they found beta radiation, and there are other sources of beta radiation. There's known background radiation. And so it's not just that is any general audience, any audience who's listening to this, and even he tricked me my first going through, right? And I have a background in physical sciences. I've taken a geology class, right? It's very difficult, right? You have to have a lot of technical knowledge to understand why that was an incorrect statement. And there's not a lot of people who are able to do that,
Right.
if that kind of makes sense. That's not just oh, somebody didn't bother to look it up. This was a pretty technical detail that you have to have a lot of know-how to identify where the falsehood was. So.
Yeah, absolutely. And you also have not only background radiation, but cluster decay as well from other nearby sources, which, from what I understand, could also be a potential source for carbon-14 and coal and diamonds, correct?
Yeah, so it is also possible. There is lots of stuff that's radioactive here in the dirt, right? Dirt, super radioactive. Granite, especially. Granite is very radioactive. Actually, the people in the United States, the workers who are exposed to the most radiation as part of their job, you'd think it was people that operate reactors or airline pilots, but no. It's ticket takers at a very specific stadium in New York somewhere, because the stadium is made of granite that has a higher than normal uranium concentration.
Interesting.
Yeah. So if you have something like a diamond, so carbon-14 is produced when it's produced from nitrogen-14, right? It's an interaction with cosmic radiation and nitrogen-14. And when carbon-14 decays, it decays back to nitrogen-14. So if you imagine in a diamond, right, or something that's hard, something where diffusion is going to be tricky, if the carbon-14 that was present decayed, it turns back into nitrogen-14. If you hit that with some high energy photons, that can happen at certain places, say deep in the earth, next to a big thing of granite and you leave it there for a while, right, it can get hit by these high energy photons. Normally, carbon-14 is made by interaction with cosmic radiation, but any high energy photon will do, such as those released when uranium and other heavy elements naturally alpha decay. Does that make sense? Sorry, I didn't mean to get super technical.
Oh yeah,
Okay.
yeah, that makes sense to me.
Yeah. So that is less, that can happen. It's kind of less of an effect. So it is possible that they could have dug up a diamond, put it through a mass spec, and found carbon-14, right? That is possible, but probably what they're measuring is the constant background radiation that's potassium decaying into argon.
Awesome. And another thing that is interesting to note of these diamonds that Dr. Snelling likes to tout is when I was going through the Answers to Genesis blog, I noticed that most of these samples were much older than 50,000 years, which anyone who knows even the most rudimentary thing about carbon dating would know that anything past 50,000 years is just carbon-14 is simply no good because there's so little carbon-14 left in the sample.
Exactly. Yeah. So in general, any dating method, any radiometric dating method is good for about 10 half-lives of the parent. So, and past that, there's just too little to measure. So something like uranium to lead, that's great because uranium-238 has a half-life to lead of 4.5 billion years. So we've had maybe one half-life passed. So that's a great one. But carbon-14, its decay constant is, its half-life is, I think it's 5,700 years. I usually say about 6,000 just because round numbers are easier. So it's only valid back to like 60,000 years. And the calibration curve is good back to 55,000. And so what's interesting is when he talks about these things, like, he'll say, oh, we have these samples that are too old to still have carbon-14 in them, but we found carbon-14. And again, what I think he's referencing there is, they measured background beta radiation, probably from potassium decay.
Right. So
and
basically,
go ahead.
Sorry to cut you off. So basically, his whole argument is there's carbon-14 where there carbon-14 should not be, therefore young Earth. That's pretty much his entire. You can boil
That's basically it. Yeah. And then the other thing he'll do is he'll get like, oh, these two samples are supposed to be millions of years different in their ages, but we measure the carbon age to be the same, and they're both like way too old, in the millions of years old. So they're too old to be radiocarbon dated. So again, if you're measuring a constant background radiation, that would give you the same radiocarbon age, right?
Right.
So it's, yeah, that's oh gosh, it's either like woefully ignorant and uneducated on the tools that they're using, to the point that like he should get his money back for his PhD, right? Or knowingly deceptive. Those are the only two conclusions that I can figure out.
Yep. And just out of curiosity, Dr. Andrew Snelling, have you looked at any of his papers that he actually published in respected peer-reviewed journals, or looked at his PhD thesis?
No, I actually haven't looked at any of that stuff.
So what's interesting, especially about Dr. Snelling, is when Dr. Snelling is publishing in the peer-reviewed literature, there's no indication anywhere that he's actually a young Earth creationist. And he even points out that, yeah, these dates look, this does look like it's millions to billions of years old. So it appears as if he is being purposely deceptive of his audience. The real Andrew Snelling, please stand up. This is an article from No Answers in Genesis, and I will put this in private chat, in the sidebar chat. Private chat, in the sidebar chat, okay. And Snelling and in one of his papers here, the oldest rocks in the Kungara area, domes of granite, i.e. to geologists, this means that they are 2,500 million years old. The Archean rocks were all briefly buried in between 180, 1870 and 1800 million years old, from his writings and the actual peer-reviewed literature. So he's kind of speaking out of both sides of his mouth. There's Dr. Andrew Snelling on anthropogenesis, touting young Earth creationism, and another Dr. Andrew Snelling saying, no, it's not. So.
Mm-hmm. Yeah. And so that's, I don't really, that's kind of hard to defend, and it is definitely true that like, that Snelling couldn't get his young Earth creationism ideas published in a real academic journal, like not because of bias against him, but because of the low quality of the science, right? I am not a geologist and I can find flaws in his methodology, right?
Oh yeah, absolutely.
And yeah, just to get there, I know there's sort of people that will say, science publishing is biased against creationism, and it's not really that. It's more, there is no good, robust science that supports young Earth creationism.
Exactly, and it's like saying that the literature is stacked against flat earthers. Well, of course, what do you actually expect? They're not going to take their arguments seriously for very obvious reasons.
Right.
And you're more of the geology and planetary science, and the field that I will be studying is biology. Dr. Dan and myself did a couple of videos on Dr. Jeanson's claim of a recent mitochondrial DNA being 6,000 years. Not sure if you've seen those videos or not, but even I, just transferring into university and not actually having taken any biology courses at UMBC, I can already pick apart some of the major flaws within Jeanson's paper, or I should say blog post.
Yeah, and that's, it's on the one hand, like you and I don't find these arguments difficult to pick apart, but I also never want anyone who like believed any of these arguments to sort of feel dumb, right? Like, if you believe something because someone you trust taught it to you, right? If you later find out that it's untrue, that's on them. That's not on you, and that's always my hope, right? That's one of my hopes of putting out videos that's like debunking and things like that, is to, again, put out good information for anybody that's looking for it. And yeah.
So with Earth Day approaching, I feel this would be a good time to kind of talk a little bit about the climate and the environment and
Great.
some of the stuff about climate change and global warming. Can you tell us a little bit, for those who might not be familiar, about what actually is the difference between global warming and climate change? Because I know that these are two different terms that mean two different things, correct?
Yeah. So global warming, climate change, both would be accurate to describe what's currently happening to our planet. But climate change is a little more of an inclusive term, and it's used because, so if you look at the average global temperature of planet Earth right now, it is increasing, and it is increasing at it's really fast. It's increasing real fast for climate and geologic timescales, right? And it's really the rate of the change that's the biggest concern, right? Like I shouldn't notice climate level changes in my lifetime, right? And no one person should. So climate happens. Climate is talking about signals and trends, right? Things that happen over like 50 years, over many decades. So, we do have some decadal variations, but we're talking about long-term trends, long-term changes.
Right.
So the pattern, right? If you just look at average global temperature, temperatures are going up. The however comma there is that there are a few places where you see temperatures decreasing, and that can happen like locally. So there's like in Antarctica, right? And that has to do, we're pretty sure climate change in Antarctica going has to, like there's places where ice is increasing and has been for like the last 10 years. We're pretty sure that has to do with ocean circulation trends that goes over, they have it over decades is the time span. We haven't been observing Antarctica consistently for that many decades. So there's a lot of things we don't know. So climate change is kind of an easier term to use when we're acknowledging that this is real scientific, Earth real big, right? So how climate change is going to affect, say, Southern California might
Right.
look very different than how it's affecting Norway. So Southern California is going to see it's become more and more desert-like. That's what we would expect there. But Norway, we might expect warming temperatures to lead to melt, to lead to maybe more precipitation. That one I'm kind of thinking off the top of my head. Southern California is one that I know. I don't know why Norway was the second country that popped into my head. So climate change is going to affect different regions differently. And so global warming is a little bit of an oversimplification of the complexity of the problem. Hope that makes sense.
Yeah, definitely.
Okay.
Yep. And what do you feel are the biggest challenges in combating climate change and preventing runaway global warming?
Runaway global warming. Yeah.
And,
Um,
and I guess, would you be able to explain what these terms mean?
Sure. So runaway global warming is there does reach a tipping point, a kind of point of no return. Um, so Venus is a great case study of what runaway greenhouse gases look like. It's where you get this like positive feedback loop where the warmer temperatures lets more carbon into the atmosphere, and it just spirals out of control. Um, and we're not there, right? But I think some of the biggest challenges is that uh, noticeably noticeably reducing carbon emissions, which is there is no debate, right? There is no debate amongst scientists that the primary cause of climate change is anthropogenic, man-made um, carbon, fossil fuel, carbon being released into the atmosphere. That's not in debate, right? Um, and the hardest thing there is that you and I could go completely carbon neutral, never drive a car, never get in a plane again, right? And make absolutely no difference, right? Because what we need are like the groups that are pumping carbon into the atmosphere are like large companies, right? So there's kind of, you and I probably grew up with like the I don't know, children's TV shows singing at us to like make sure you recycle and turn the water off when you're brushing your teeth, right? All these ways to like be good, responsible citizens and conserve. And the fact of the matter is that like every consumer could be as responsible as they possibly could be, and it make almost no difference, right? So where you need the change is basically for the groups that it's going to cost money, right? You need change from like the fundamental practices of large corporations. We need to change like how we get our energy, you know.
Yeah.
We need to change how far we ship our food before we eat it. That's a huge contributor. So like the way we transport goods, the way we produce goods, these are not problems that you can really solve at like a grassroots scale. These are big, big global country-sized problems. So we need buy-in not only from global like leadership of all nations, right? Because again, you could have somebody like France that gets almost all of their power from nuclear energy. You have other countries that are going like completely carbon neutral. That's great, but like one country does not fix the problem for the whole planet. If you sort of need everyone to buy in, and that's going to cost money.
Yeah, and
Right.
Rainbug asked the question in the cyber chat. What do you think of sustainable insect protein? I am not quite sure what that is.
I actually am. So one of the biggest contributors to carbon is cows and other meat products because they use a lot of resources. Cows especially produce a lot of methane. Methane is also a very methane is even better at being a greenhouse gas than carbon dioxide is. We just don't emit as much methane. So they emit a lot of methane, they use water, they use resources, right? So like eating your hamburger, right, has a pretty high carbon cost. And so if we can switch to something like insect proteins, which if they can actually be like sustainable. So I don't know a whole lot about like the farming practices and the carbon footprint of insect proteins, but if you can get some of your protein from bugs instead of cows, that's going to lower a carbon footprint. So if you can make that, and it also addresses food shortage issues, right? So if we can not be grossed out by the creepy crawlies, that can be a good sustainable source of protein that has a much smaller carbon footprint.
Awesome. And what are your thoughts on nuclear power and other green energy sources? How do those work, and what would be the overall, and what is the climate effect on these types of energy sources?
Nuclear energy solves so many of our problems. I am a super pro nuclear energy. I would oppose, like, my biggest problem with the Green New Deal was that it didn't include nuclear energy,
Yeah,
right?
and I would agree with you 100%. I am very much pro nuclear energy. I love
Yeah,
nuclear power and I think it should be. And we absolutely cannot solve climate crisis without utilizing nuclear power.
exactly. Nuclear, it's safe, it's clean, it has like the least impact on the environment of anything. You know, you are in the United States, if you live within 50 miles of a civilian nuclear power plant, right? Your average radiation exposure is for a year is the equivalent of eating half of a banana, right? If you compare that to your radiation exposure, if you live within 50 miles of a coal plant, because the exhaust from a coal plant is radioactive. It's not just carcinogenic, it's straight up radioactive, right? That's, I don't even know. It's like it's at least 100 times, you know. So like we think of things like coal as, oh, that's so much safer than nuclear, and it's just not. It's just not. I would never want to live within 100 miles of a coal burning plant because it's so dangerous. And
Um,
I have personally hugged a nuclear reactor.
and absolutely. And when you actually look at the death counts related to nuclear power, comparing it to others, nuclear
Yeah.
power has caused far fewer deaths than coal and other types of sources as well.
Mhm.
So that
Even
is
when you
also
look at even when you look at like disasters like Fukushima, there were exactly 0 deaths related to the reactor accident, right? There was no radiation related deaths from Fukushima.
right.
Um,
And
it
then
was an
compare
expensive fail, right? It cost a lot of money, but no one was harmed.
Right, of course. And in comparison, we have maybe 3 or 4 major nuclear power disasters. Compare that to the hundreds and hundreds of disasters from pipelines, coal, stuff like that, people dying from black lungs and stuff like that, and um, the BP
Absolutely.
oil spill a couple years ago. So, can you explain a little bit about how nuclear power plants work and operate?
Yeah, absolutely. So the basic idea, by the way, Chester just had his dinner, so he's a happy boy.
Oh,
So the basic idea is you use either in the U.S. these are all going to be uranium plants. So you go to your friendly neighborhood uranium mine, you dig up some uranium, um, and you do want to enrich it a little bit. So uranium comes in two main flavors: uranium 238, which makes up the vast majority. It's 99% of naturally occurring uranium is uranium 238. After that, the next naturally occurring isotope is uranium 235, and then there's uranium 236. But we don't really worry about 236. Uranium 235 is able to have a sustainable fission reaction. So uranium 238 can fission, but your neutrons have to be going really fast, and so it's hard. But uranium 235 is capable of having a fission reaction. So what that means is you take your uranium 235 atom, you chuck a neutron at it. That uranium 235 absorbs that neutron, and then it gets excited and it splits in two. So not actually in half. It's kind of interesting. It usually splits. Sorry, Chester would like to pull my headphones out. Um, so it splits. It's like the mass wise, it's like 1/3, 2/3. And what goes on when it splits in half, and I can't overstate how just like bonkers reaction, bonkers situation is going on, that an atom just like says YOLO and splits in two, right? That doesn't happen very often. Some of that atom's mass is then converted into energy, right? This is E equals mc squared. So what that means is, like, if you weighed the uranium 235 atom you started with, and you weighed the two pieces left over after it split in half, the sum of this mass and this mass doesn't equal what you started with, right? You lost some mass. That mass was then turned into energy. And as far as we as humans know, this is the most efficient way. You get the most bang for your buck in terms of like turning something into energy. This is the most energy dense thing that we know exists, right? And so that energy has to go somewhere. And what it does is it makes your fuel hot, right? That energy is just expressed as heat. So then you usually have water that comes by and it removes the heat. And then, so you run water over it. The water is cold, goes over the hot rock, gets hot, moves off, and makes steam like any other power plant. Steam is then used to make turbines spin and generate electricity. So that's the basic idea. There's some very cool innovations in reactors. France and other places in Europe have breeder reactors, which means they can reuse some of their fuel, which is amazing. That reduces nuclear waste and just makes the whole process more efficient. Canada has CANDO reactors, which is my favorite name of a reactor. It's called Canadian deuterium, and they're actually able to produce power with unenriched uranium. So they just dig uranium up out of the dirt. They don't have to enrich it at all. That enrich it just means you want more uranium 235 and less uranium 238. So you remove some of the 238 and keep more of the 235. That's the enrichment process. Canada is able to do this with unenriched uranium, and it's the enrichment process. It's actually the most expensive step in the pipeline. And they do this because they use heavy water as their coolant instead of regular water. They use deuterium. So that's very cool. And again, nuclear power it's so safe. Usually people ask, like, what do you do with the waste, the spent fuel? A lot of times it's stored on site, and that's pretty darn safe. There's also a proposed site in like a mountain, Yucca Mountain, Yucca, yeah. That was shot down. For silly political reasons. But like we could have a big one place where we store all of our nuclear waste in a very safe way. We've had and I also like to point out to people that every submarine and carrier in the United States Navy has been powered by nuclear reactors since the 50s. Right? These are operated by 18, 19-year-old kids who go through a lot of training, right? But that's who operates them, and we've never had an accident, right? There's never been an accident on a U.S. nuclear ship. And they've been operating for, 70 years straight, constantly, with no problems. So, like, if you want to look to a record of safety, right? Like, we as a country know how to do this. And we have lots and lots of people who are really expertly trained in how to operate nuclear reactors incredibly safely. So yeah, support nuclear power, support veteran jobs. There you go. It's a straight nuclear to civilian land pipeline.
Yeah, and my personal favorite thing about nuclear power plants is that you can power so much in such a small piece of land compared to solar power or wind power when you need to utilize so much land space for so little energy.
Yeah.
Now,
I'm all for solar and wind and like other forms of energy. Like I'm great. Nuclear is also part of this equation, yeah.
Yep, absolutely. And for those I'm concerned, there's been a lot of concerns from how uranium is actually mined and what impact that has on the overall fossil fuel and stuff like that. So would you be able to explain that a little bit to us?
I don't know a whole lot about the mining process, to be honest. That's a little outside my field of expertise.
Yeah, that's not a problem. So yeah, we are, of course, getting ready to start hurricane season in the next few months, and 2020 was a pretty bad year for hurricanes. Thankfully, we didn't have too many bad ones actually make landfall. So, what exactly are hurricanes and how do they form?
Awesome. Yes. So hurricanes are actually really cool. So if anybody in the room has ever taken a thermodynamics course, a hurricane is the closest thing to a perfect Carnot cycle that exists in anywhere. So a hurricane is fundamentally a heat engine. You've got warm ocean water. Warm ocean water makes warm, moist air at the surface. What does warm, moist air want to do? Rise. It's going to rise. It's going to make a cloud. And when and then it's going to eventually, like a lava lamp, make that cloud, get rid of its moisture, and then sink. And we start to get a nice convective system going. Now, this is over the ocean. These are really big systems. The radius is like a few hundred miles. So this is big enough that it's actually affected by the Earth's rotation. So that's why a hurricane starts to spin, is because it's feeling the Earth's rotation. I actually just did it backwards for the Northern Hemisphere. In the Northern Hemisphere, the hurricane, hey Chester, is going to spin counterclockwise. In the Southern Hemisphere, it's going to spin clockwise because of the Coriolis effect.
I would love to see how flat earthers explain that.
Well, apparently it's something called an electromagnetic wake, but I've yet to get one of them to explain what that is to me. So I'm working.
Yeah, I'm sorry, I had to take a little bit of a snarky swipe at flat earthers.
That's fair. That's fair, man. Um, so hurricanes are really interesting. You for one to form, you need to be off the equator by about 5 degrees. Hi, buddy. You need to have a pre-existing low pressure system. These are pretty common off the coast of Africa. So you need a pre-existing low pressure system. Low pressure systems help give us lift, and that's a thing that you need. You need to have ocean temperatures sort of warm enough, and you need that ocean temperature to be warm down for a decent depth in the ocean. Um, and you need to have weak vertical wind shear. So if your winds are too strong, the horizontal winds are too strong, then it can sort of knock over that convecting cell and not let that big thing develop. Um, it is. We're getting up on hurricane season. So definitely a good time for everybody on the east coast of the U.S. and other places to be weather wise. Now, the great thing about hurricanes is that you can get a solid 3 to 5 days heads up of when they're going to make landfall. So if you go to the National Weather Service, that's like nws.com or weather.gov, the National Weather Service, they'll put out their like forecast tracks. Their tracks are very good and very reliable. I personally don't like it when news stations put out. Have you seen the spaghetti plots? If I say that, do you know what I'm talking about?
From the spaghetti bots, I mean, from what I understand, those are like the little graphics that show, okay, this is where um, the storm could potentially hit, correct?
Yeah, so it's this plot of like, oh, hey, this model says it's going to go here. This model said here. And so it's a plot of like lots of lines of all different possible tracks. Um, the reason that I don't think it's very responsible to show those to the general public is because not all of those paths are equally likely. And you
Right,
have to know a lot about specifically tropical meteorology and how numerical weather models work to understand why one might be more likely than another.
right,
It's just, it's not readable by the general public, but it feels readable, if that kind of makes sense.
right. And it's definitely not readable by a former somebody that decided to
Mm.
um, use a Sharpie to
That made
to
me so mad.
oh
Fun
yeah,
fact, it's actually a felony to like change a National Weather Service forecast to deceive the public,
yep. So
if
another
you were wondering.
yeah,
Because go ahead.
so that right then and there should have been an impeachable offense. So
Mhm.
yeah,
And the reason that's a felony is because the National Weather Service, the whole hi Chester, the whole purpose of the National Weather Service, its mission is to preserve life and property, right? That is the whole goal. And the National Weather Service is an organization of very dedicated, very well educated scientists whose whole goal is trying to keep the people right safe. Part of that is ensuring that the public can have confidence in our forecasts, right? Because otherwise you get in a boy that cried wolf type of situation, right?
right,
Um, so that
yeah,
if we say a hurricane could come your way and then it doesn't, and we say a hurricane could come your way and then it doesn't, and we say a hurricane could come your way and then it does, that third time you're probably not going to believe us. So a lot of time and energy goes into how the National Weather Service presents and reports forecasts.
exactly.
Yeah.
And when President, um, I'm not gonna say that somebody's name, but
Yeah.
when they did that thing, that of
Hmm.
course put a set panic in for the people who lived in that general area. When the
Hmm.
reality is, that area was not going to be affected by the hurricane, and that's pretty much exactly what happened.
Exactly. And what's worse than that, though, is that National Weather Service office then had to stop and devote resources to reassuring the people of Alabama that they were safe, that they didn't need to take action, when all of their attention should have been focused on South Carolina and Georgia and North Carolina, where the hurricane was actually coming to, right? So resources are always finite, right? And time is imperative, and time is precious when you're forecasting hurricanes, tornadoes, right? The timeliness matters a lot in those scenarios. And yeah, that one really bothered me. There's lots of things about that president that bothered me, but that one was just it was so unnecessary and it was so dumb, right?
Right. And of course, it's a slap in the face to the scientists who actually have done the research and have done the work. And basically, he's telling them, say, "Hey, I know more than you guys do."
Right. And again, these are public servants. These are people who have devoted their entire lives to that mission of preserving life and property. Right. The National Weather Service is just a bunch of nerds that want to help you. Right. That's all we are. I'm not part of the National Weather Service, sorry. But what's really cool about the University of Oklahoma is the central hub of the National Weather Service is the National Weather Center, which is the building that my school is in. So I'm on the 5th floor, right? And the 4th floor is like NOAA and National Severe Storms Laboratory, and all kinds of stuff. So we partner a lot with the National Weather Service and NOAA more generally. And so I know these guys, they were all mad too.
Oh, of course they were. And trying to think what else. So you're right here in Tornado Alley. And I know there's been from what I understand, pretty bad tornadoes recently. So what exactly are tornadoes and how do they form?
Awesome. So tornadoes are so interesting. Okay, so I said earlier, a hurricane, you can get like 3 to 5 days in advance. You're going to know where it's going to make landfall. For a tornado, the gold standard is 20 minutes heads up, right? So these systems are much smaller, right? So they're maybe 50 kilometers across. I'm sorry, when I do science, I think in the metric system, but when I when I like drive places, I think in miles, but I can't translate between the two. So it's tens of kilometers across. So it's much smaller. And one big storm system that's capable of producing a tornado, right, is so not every system that's capable of producing a tornado will produce a tornado. And a lot of times, if it's capable of producing if it does produce a tornado, it's going to make several. That one's kind of interesting. So for these guys, you need. So it's kind of the same idea where you get it's a spinny thing, right? And to make one, you need a very strong lifting mechanism, right? So when we talked about the hurricane, I talked about you have a big convecting cell like a lava lamp. That's the same type of thing we want so that we're trying to make if we're trying to make a tornado, but on a much smaller scale. And so we need a stronger lift, right, than what you get for than what like just warm ocean water provides for a hurricane. So generally what you're going to get when you're going to get a tornado, you need basically you need warm, moist air and cold, dry air to sort of smash into each other violently. And the bigger the difference between the temperature and the amount of moisture, the easier it's going to be for that lifting mechanism to take off. Okay, so that's how we just start to like make a thunderstorm, right? If we want to actually make a tornado, we need some strong surface winds, and we need those surface winds we need horizontal vorticity. We need some rotation at the surface. So we kind of need rotation that looks like this. And what you do is you get some strong winds, and they pick that spinny thing and they tilt it on its side, and then we get a spinny tornado. Tornadoes are actually a lot more complicated than hurricanes.
Yep.
Um, yeah, they're gonna come. You need a strong thunderstorm first, right? So you get your strong thunderstorm first. Did your brother not want to cuddle you? Did he not like it when you sat on his face? Yeah.
Yep.
Uh,
By the way,
yeah.
since you're a meteorology person, you would know this better than anyone. You're of course familiar with the heat problem with the Noachian deluge and all of their
Yeah.
creative rescue devices. I'm not sure if you know who a guy named Standing for Truth is, but he has a
I know
very
of
creative,
him.
yeah, so he has a very creative idea of how the heat could have been removed, and that is from hurricanes. That somehow hurricanes would have been able to somehow alleviate the effects of the Noachian deluge. Now, now Jordan did a little bit of a what if and did some
Mhm.
calculations and said, okay, in order for that to happen, they would need about 180 meters of rainfall per day for these wall-to-wall hydrogenes for the model to work. So lots of problems with it.
Mhm.
But the more important question is, if there was somehow a global flood, could this global flood have even been able to sustain hurricanes?
Um, oh my gosh, there's so many things wrong with that idea. Um, um, okay, so one, hurricanes are very specifically tropical storms, so they're not gonna they form in the tropics. They form south of 30 degrees, right? Um, two, uh, they don't remove heat; they move it around, right? So equator warmer than the poles. Hurricanes are one of the ways we transport heat northward, right? But the atmosphere has four distinct layers: the troposphere, which is where we live and breathe; the stratosphere; the mesosphere; and the thermosphere. But just think about the troposphere, where we are. It's you can think of the barrier between the troposphere and the stratosphere. You can think of that as almost a cap, like a hard boundary. So a hurricane extends up to the boundary of the troposphere, that's called the tropopause, and it sort of hits it and then it comes back down, right? So the heat problem, you need heat to escape to space, right?
Right.
Hurricanes don't do that. Hurricanes stay in the troposphere. So they're moving heat around, but they're not removing any of it out of the troposphere into the stratosphere, or the very little transport, right? Don't at me, weather Twitter. Um, and they're transporting it from the equator poleward. But if you're talking about the heat problem of the of Noah's flood, that's more than enough to vaporize all of the oceans.
Right.
So you're not going to get a hurricane if you don't have an
An ocean.
ocean.
And
Um, yeah.
you're not even going to have a planet, so forget an ocean.
Right, right. So you would need that, like a hurricane with that amount of heat. A hurricane couldn't even form, um, because like the heat would destroy it, right? Um,
Right.
yeah. So I'm not quite sure what he's going for there. That's
Yeah.
that's like that's asking if like, let me see what's
Yeah.
a good example. Could I mean, I guess it's kind of like asking, could a windstorm protect you from a nuclear blast, right? Like it's just order of magnitudes, not the same.
Yeah. Maybe I'll see if I can find the section where he spoke about that, and
Yeah.
just so you can hear his entire arguments. Um, so here is basically the argument. your audio. And I'm going to mute myself so it doesn't echo.
Okay.
The effects of the Genesis flood, massive hurricanes during the flood would have actually taken up much of the heat into space. Okay, and this isn't post hoc ad hoc. I want to say this before you continue, David, because today we can see what? We can see hurricanes, and we can see how great they are at dumping heat and energy into the space, into space, okay? For example, here I've got jotted down, when a hurricane goes over the ocean, what happens? Well, the temperature itself actually drops. And not just a little bit, it drops significantly. Okay, David?
So it depends on how you measure it, right? Clouds are shiny and reflect sunlight, so you're going to see it as cold. Two, this has to do with latent heating. So when you I always have to think about this to make sure I don't flip my directions. When you rain, right? You get some latent heat release. So you do get like local rain. There's a reason it feels cool after it rains. The energy of the water going from a gas to a liquid, right? It's going from that heats it up, other way around. That's good. Because that's going from a more energetic state to a less energetic state. So the energy had to go somewhere. Evaporation, you go from a less energetic state to a more energetic state. So you had to sort of give away energy. You took energy from the environment and you put it into the water to make it evaporate. I know that I just explained evaporation in the most complicated way, and we all learned this in third grade. But my point there is, so latent heat of evaporation, you're going to see a local cooling effect. That's not, that heat didn't go anywhere. It's stored in the rain, right? And it comes back if that water vapor condenses into the rain, right? So that's just like latent heat release. And so I'm not, it's just, also, I mean, I think their argument, that cooling that he's describing there it's not removing heat like from the environment because of the massive tectonic shifts that are in theory going on with the flood. It's just the how energy is being stored differently when water changes phase, and so that's not a heat sink. That's not removing heat from the system, which is what you need with the breadth of heat problem, is that there's too much energy and you need to siphon it off and put it somewhere. Latent heat is not going to do that. And a hurricane is not going to do that. It's good. Again, it can move that heat around, right? But it's not removing energy from the system. I hope that made some kind of sense.
Yeah, I'm just going to continue playing with heat this here.
Okay.
So, it's understood by most scientists that convection is a great way to move heat quickly. And that's all we're saying is, as long as this heat, this abundant amount of heat is moved quickly and into space, okay, we know there would have been a lot of convection during the flood year. Look at hypercanes, for example. Okay.
So that's pretty much, and of course, if you notice something, he does not provide any mathematics behind it. What is the math? Right. How much what this hypothetically have been removed? There's no math behind it. It's just ad hoc.
And and he did say something there that he said that we know hurricanes are good at moving heat. I'm actually fine with that. Like it's a very efficient engine. It's good at moving energy around. But then he said that's what we need. We need to move that heat to space. Hurricanes are not good at moving energy to space. That's not what they do. They move heat around in the troposphere. They're not adding to what's radiated to space.
Right.
Yeah. So
All
that
right.
was nonsense.
Yeah, so much nonsense, so little time to unpack it all. So with how big the Earth is and with how much water there actually is, would there have been enough water to begin with to be able to sustain a 40-day rainfall everywhere on the Earth at the same time? What is that even meteorologically possible?
No, it's really not. Um, so, okay, because let's just think about this in terms of we've got water in the ocean, right? And if we want it to rain, right, we need to evaporate water, move it up, have it condense, and then rain, right? If it's going to rain here in Oklahoma, we had to get that water from somewhere, right? So that's coming from generally over the ocean. Obviously, you can like evaporate from lakes and rivers, but let's just think globally, very big picture for a second. So if we want it to, rain over all of the land, right? We have to have rising motion from the ocean, and making those clouds, and then they need to move somewhere and then rain, right? Um, so 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 you have to have if you have to have rising motion somewhere, you're having sinking motion, right? Because we gotta finish this out. Where you're having that sinking motion, there is no rain. That's a high pressure system. That's not where you get storms. You get storms like over the rising leg, not over the sinking leg. Um, and that, by the way, is why it's very rainy at the equator and very dry in the Sahara Desert, because globally we have a rising motion at the equator that moves northward, and then it falls and hits about 30 degrees north, where like the Sahara Desert is, right? So you have a global high pressure system there. So I have no idea how they propose that we basically have rising motion over all bodies of water, right, to keep feeding this giant storm, but it always goes up and that air never falls, right? Because that's what you would need for it to rain everywhere, right?
Right.
It doesn't, you can't do it. I don't know if that makes sense, because it literally just comes down to what comes up must go down, and where
Right.
it goes down, it's not going to be raining.
Right, of course.
Yeah.
And too many problems for the global flood to even get off the ground.
Yeah. It's not feasible. It's not physically possible, and it doesn't have to be, right? Like you don't need to make it literally true.
Right,
and
exactly.
yet and something I like to point out whenever I'm talking about young earth creationism is that the majority of scientists globally, right, practice a faith of some kind, right? And the majority of people of faith in general and Christians accept an old age of the earth, right? So this is often framed as like Christians versus atheism, and that's just not what's happening, right? This is one incredibly small sect of Christianity, right? Against people of all different types of faith, right? Who happen to be scientists.
Right. And of course, you get people like Dr. Miller and Dr. Francis Collins, who have made enormous contributions to science, who are both devoutly Christian and obviously see no problem. So this is very much a very small sect, but unfortunately, these people in Congress and in our leaderships who actually believe in young earth creationism and science denialism, and these people and these belief systems are doing real harm
Mhm.
to public policy.
Yeah, definitely. And I mean, I'm pretty open about this on the internet. It does not matter for how I do my science, but I happen to be a Christian. I'm Episcopalian, the chillest of all Christians. And it's just, there's literally never been a conflict between my faith and my work, right? It's literally never come up, you
Right.
know? So the idea that there's this like huge battle going on is just nonsense. It's just not reality.
Right.
And yeah, science denialism in general is absolutely harmful. And what really, and I think that puts responsibility on people like you and me and scientists as a whole, and especially science communicators to, like I think we really should ask ourselves, like, what can we do to build trust between our professional fields and the public, right? Because that's fundamentally what it is. I think that's what science denialism it boils down to is my expertise is somehow not trusted. And so my question there is, well, why and what can I do about that? Right.
Right.
So I think this is a really important question. That's also partially coming from meteorology, where so much of meteorology is, we could have a perfect forecast, but if we can't get anybody to listen, it doesn't matter, and so I'm really lucky that in my field, communication is so emphasized. And I think that's really valuable. And I think more scientific disciplines should put focus on good communication, building public trust.
Right. And we've been going for about an hour, and so this will be probably a good place to start wrapping things up. If you had anything you wanted to say, or want to plug in anything that is coming up on your channel.
No, if you want to pop over to my channel, every Sunday I've got a new video on climate dynamics. So those are more lecture style, but I'm trying to take a big complicated topic and break it down into some bite-sized pieces. Again, that's accessible to everybody. And then on Wednesdays are sort of more fun type videos. So I just had one up that was, I interviewed Erica and we talked about what primatology is. And that's also when I do like debunking videos and
Yeah.
whatnot. With any luck, I should be actually debating Kent Hovind on Monday.
Interesting. And
So
and it looks like on Tangelo Grosso in the comment section said, Maddie dodged to have a conversation with me.
oh, I didn't intend to dodge a Tangelo. I'm still super open to that. It's just that I don't think we found a platform.
I would be
So
I'd be very happy
yeah.
to host the discussion. If you're interested, I would be very happy to host.
Yeah, I'm still super open to have that conversation with you, Otangelo. Let's just reach back out. If you're still down, let's reach back out to Dino. I know Modern Day Debate wasn't going to be up for it. I think his schedule is just booked.
Yeah. And to be honest, I don't think James is doing much of younger creationism or evolution debates recently
Yeah.
because, from what I understand, they're just not that enjoyable. And
Yeah.
I can definitely understand why people don't really like those types of debates. But yeah, from what I understand, James isn't really going to host evolution versus creation stuff. Hello, Dr. Dan. Good to see you. Thank you for stopping by. Jorge, thank you so much for stopping by as well. Anyway, that should be a wrap. Thank you so much, ScienceSideUp, for joining me, and I certainly hope you come back and definitely should do this again.
Yeah. Thank you so much for having me. This was a blast.
Yep, absolutely. All right. Have a good night, everyone. We are out of here. Have a good night.